Something about gasification. I will not go in depth to the gasification, but there are like few points. The mainly it's in this context, so it's a gasification of biomass. So gasification can be used also to other carbon containing materials, also fossil based materials in principle. And I know that, for example, in addition to biomass, so recently there are studies related to gasification of waste materials like waste plastic and such kind of things. And the bigger picture here is that biomass can be gasified or converted into synthesis gas. So the main desired product here is mixture of carbon monoxide and hydrogen, and that's often called syngas or synthesis gas. And it's a mixture of very simple components. So there is a carbon source, carbon monoxide, and there is hydrogen source of hydrogen gas. And in this context, so there are few reactions that it can be converted into fuel components, and this we'll take a look at next week. But one process mentioned already several times is the so-called Fischer-Tropsch process, and it utilizes synthesis gas to make alkenes and other hydrocarbon products. Also, where synthesis gas is starting material is methanol, which can be used as fuel, but it's of course the basic chemical that has many uses, and it's produced in huge quantities. Also, synthesis gas can be enriched or purified with water gas shift reaction to make hydrogen, and this is something that the hydrogen production is discussed more in the Power to X course, where the hydrogen production is also a key part. Gasification process contains various steps, and this is of course understandable that biomass like storage and transport to the facility, and then you need to, if the biomass is large, so you have to process, mill or grind the particle size into suitable so that it fits the process, and that depends of course on the type of process, type of reactors that are used. So but in any case, some kind of pre-treatment and pre-processing steps. So side reduction, drying, so removal of water. If it's fresh biomass, so it contains like and roughly half of the mass is just water, so it should be dried, and then it's feeding and the actual gasification, where a mixture of products is formed, and then it's product recovery and cleaning, and also ash disposal. This comes from the inorganic materials during gasification. So the biomass contains this inorganic, like sodium, potassium, magnesium, which oxidizes into converts into different salts during this process. gasification is by no means any new technology. So biomass and solid carbon coal has been treated already earlier, and this so-called synthesis gas or producer gas has been produced, and it contains, depending how it's done, so it's always a mixture of these quite simple ingredients, or these are the targets. So carbon monoxide, hydrogen, you end up with some CO2, methane, and of course if you use as the oxygen source or air, so you always have nitrogen in the mixture as well. This illustrates a picture that sometimes this, at least in Finland, and it says that in Europe as well. So these cars were used like in 1940s that utilized this gasifier to make the fuel out from coal or such fossil-based materials. Pyrolysis is basically breaking of that carbon-containing material at high temperature in the presence of small amount of oxygen into chemicals or components, and it can contain just a second. Yeah. So the reactions, or this, if you use thermal decomposition, so basically this is just when you heat up material high enough, so organic material starts to break to different components. And here it says that it's without oxygen or steam, but you can also do it so that there are small amounts of oxygen or steam present, and you can get different types of products in principle. And for example, in biomass gasification, there will be always some water in the biomass itself already, so that also is possible to end up with this so-called steam reforming reactions, which incorporate the water in the reactant side. So the biomass can decompose thermally by itself, in principle produce products. It can react with a small amount of oxygen, and this idea is that it's partial oxidation. The aim is not to combust the organic material, but just partially let it react with oxygen to form these products that can be seen here, and or react with water. Basically, the reactions are quite simple, and this table here contains the main majority of these reactions. So it's most of these pyrolysis, partial oxidation, steam gasification or steam reforming reactions are drawn or happened with the biomass and some other reactants, and then also these water gas shift methanation, it can happen between the formed products there, so carbon monoxide and water or carbon monoxide and hydrogen can react with each other. And this is maybe oversimplification, because in that process there are a lot of reactions taking place. Okay, these same reactions were in the table. So this is the water gas shift reaction. This is the methanation reaction. But the bigger picture is in this maybe slightly complicated graph. But there are, like, on the x-axis here is, let's say, the conditions, like how high or severe is the temperature, how long is the residence time in the pyrolysis reactor. So these parameters have a lot of influence what type of reactions and what type of products are obtained. So there are like a lot of reactions taking place, and if the residence time is very short, so you get just these primary products from the biomass. But if the residence time is longer, so you start to get secondary products, that means that these primary products can react with each other and form other secondary products. And if the reaction time is much longer, there can be also additional products that are formed. And the y-axis here is also the illustrated that you can obtain gaseous products, liquid products, and solid products by just tuning how you operate the reactor, the temperature, residence time, and so on. And one can make these gaseous products and synthesis gas, but you can also get some liquid products, or you can aim or want to get really just solid carbon out from that gasification. So there are various possibilities. So actually the idea is here more or less what I tried to illustrate. So gasification, the process, can be optimized to desired products by changing the reactor conditions, residence time, temperature, heating rate, and so on. And this tells that you get quite complicated mixtures of different products in principle. These are all from the course textbook, but the primary, secondary, and tertiary stage of gasification. So in the primary stage you get products that are formed from the solid biomass. So somehow that is illustrated in this graph. It's like biomass arrow goes to these products. The secondary stage here in the middle, so the formed primary molecules or products form other gaseous products by reacting with each other. So it's not just biomass breaking into smaller components, but it's the formed components then reacting and producing secondary products. These are just some temperature regimes for that secondary reaction regimes. And now we have moved to this upper right corner to very high temperatures already. So this tertiary products can form. Also soot and coke are formed. Those are like solid forms of carbon. But okay, and here is I don't remember so well all the slides. So here is still mentioning about that bottom ash or the inorganic components. So biomass, as you know, so contains these different minerals and inorganic materials. So here is nicely illustrated these, that there is calcium, potassium, phosphorus, magnesium, silicon, sulfur, sodium. So these are in the biomass in some sort of salt or mineral form. And when you pyrolyze it, so these will oxidize. So you notice that these are all oxides. So the oxygen, like products from combustion or oxidation. And these are inorganic materials, very high boiling point materials, melting point materials. So they'll remain as ash material in the pyrolyzer. But from this slides already, at least I could conclude that there are a lot of possibilities to tune which products are the main ones. And also the other thing is that a lot of reactions are taking place, interaction between formed chemicals and secondary products, tertiary products are formed. So it's on a molecular level very, very complicated process. Tar formation has been mentioned in the textbook as a kind of a problematic in connection to biomass, especially. So tars are this kind of a sticky organic material, and it causes problems in the reactor equipment itself. So it's something that needs to taken into account. So one possibility, or there are methods how to remove or convert or destroy these tar materials, and that's a key point to get these reactors running longer. If tar table 8 here describes chemical composition of biomass-based tar material. I will not go through these chemicals, or I think it's not the point, but like these are larger, heavier organic molecules that form this kind of sticky tar material that is not that much volatile. It can be liquid, but when cooled down, it turns into a solid, and that's basically causes the problems that it will not exit the reactor that easily as the other products. Techniques to remove or tackle this tar problem is to, for example, add catalysts in the gasifier. And these certain catalytic materials, like here is this noble metals supported on support material, so can basically help to convert the tar material into some lighter materials that exit the gasifier and will not stick there onto the walls. Second approach is to mix alkaline metal catalyst in the fed biomass. So the catalyst is not inside the reactor as a fixed catalyst bed, but it's some kind of powder in the feed, and these alkaline metal catalysts are much cheaper. These palladium, ruthenium, platinum are quite expensive materials, so this cannot be used in a similar way. But some alkaline containing materials catalytically help to convert tar into useful and less problematic materials in the reactor. These are also in the course textbook. They present 3 different gasification reactors, and I think these are not the only possibilities, but the fundamental difference here is, if we quickly take a look at, there is updraft and downdraft and then fluid bed gasifiers. These 3 types are introduced in this context. So basically, updraft, the biomass flows from top into the reactor, oxidizing agent comes from bottom, and the products are extracted from top. So there goes this kind of upward draft of oxidizer in this reactor. Downdraft is fundamentally similar, except the oxidizer and the products are moving to opposite directions. So there are some good things and or let's say advantages and disadvantages in all of these. On the negative side here, for example, high tar formation and slacking potential, and in this, if you change the from upward to downward draft gasifier, so there is lower tar formation, and what I'm most common with is probably this fluid bed gasifier. I have not worked with such, but I have read and been involved with projects that contain such kind of gasifiers for biomass and also for plastic waste materials. And once the gasification is done, so the gas has to be purified and purified, and it's called conditioning. So the course textbook describes 3 different gas conditioning technologies, and those are wet scrubbing, dry scrubbing, and hot gas conditioning, and what those contain. So there are differences in the processing steps. So the idea is to remove unwanted impurities from that gas and separate impurities and so on. So it improves the gas quality so that it can be processed or used better in the next step, which would be, for example, this Fischer-Tropsch reactor or methanol synthesis reactor. But there are quite many stages in this. So if you take a look at, so there are different separators and cleaning steps, and in this hot gas conditioning, here are also like catalytic steps. So catalytic cracking, catalytic reforming, and water gas shift reaction that are taking place in this conditioning alternative. So here are more like separating of tiny particles, removing solids, and filtering out things. So it's more mechanical. It doesn't contain like catalytic or chemical conversions. I think the same applies for wet scrubbing as well. Okay, here is still, I didn't remember that there is still more slides about these different techniques. So gas conditioning. So catalyst can be used to remove the tar, and the catalyst also can help to adjust the product ratio during the reaction. So this is like basically, I think, more like the hot gas conditioning. These are all the cracking, reforming, and water gas shift reactions are catalytic reactions, and they help to adjust the carbon monoxide, hydrogen, CO2 concentrations, and so on. Here are some details about the hot gas conditioning. So what type of catalysts are used, but wet scrubbing, like previously mentioned, so mostly physical methods to remove these unwanted impurities. Wet refers to liquid, so the problem here is accumulation of wastewater, as well as you have to get rid of the unwanted material. So in that hot gas conditioning, you don't have wastewater formation, and some of these unwanted tars and particulate matter are converted to gaseous material. So that's the more or less difference. And gasification is also quite old field, and it has a lot of studies, a lot of knowledge and research being done, and so on. So it's also previously been applied to fossil-based materials, and now this latest step is to apply it to biomass. So some knowledge can be learned and obtained from the fossil gasification, but the biomass gasification brings some problems. The tar formation was one that was mentioned. Also, like the ash formation is maybe at least quite specific. I can imagine that it comes at least from the biomass, because fossil-based materials don't contain so many of these alkaline and alkaline earth minerals, and also not phosphorus and such, which is typical for biomaterial. But after this processing step, starting from storage and pre-treatment, gasification, and conditioning, like that's purification, and adjusting the product concentrations and so on. So then basically in this context, so we want and we obtain a mixture of carbon monoxide and hydrogen. And this is called that syngas, synthesis gas. And this is my last slides today. So it's just things that we take a look at then next time. But here is a collection of reactions and products that can be obtained from synthesis gas. And the synthesis gas is very versatile because you can make a lot of different chemicals out from it. Here's just some that you can in principle make hydrogen, which is just more or less adjusting the composition and getting rid of the carbon monoxide. There is the water gas shift reaction that plays a role in this, but you can get alcohols, different alcohols, then you can get different hydrocarbons, you can produce aldehydes. What we are more interested in, maybe this part of the course, is making of these alkanes. So these are hydrocarbon components which basically are the main components in diesel and gasoline fuels. So this can be made by gasification through Fischer-Tropsch from biomass. Then the very large and important industrial side is the methanol production. There again comes copper or catalytic materials have a role. So copper catalyze methanol synthesis. And if you want to further process these methanol, so you can produce again like gasoline components. MTBE, methyl terbutyl ether, is the additive in gasoline. You can refine them with zeolites, the methanol, and produce hydrocarbons, olefins, hydrocarbons for gasoline and olefins and so on. And yeah, here are other dimethyl ether can be used as fuel, but it's gaseous fuel, so it's not the liquid, but it can be used as a fuel, and methanol as such already like this direct use, so produces fuel, that liquid fuel that works well in various types of engines. Methanol has been used in some kind of racing cars, and also nowadays it's a renewable alternative in ships. But that's, I think, all from these today's topics. So next time we'll take a look at the synthesis gas utilization and, for example, Fischer-Tropsch reactions and processes. So